So today we are going to talk about the geometric model, and that's going to look slightly different from our binomial model only in the realm of what is it looking for. So what does it want to find? So remember the binomial random variable, which is what we talked about on Monday, has the number of successes in a fixed number of trials. We knew exactly how many dice they were rolling, exactly how many cards they were pulling. We had a fixed number of trials. Difference, geometric, is going to have the number of trials until you get your first success. That is your goal here for geometric. How many times do I have to roll the die until I get a heads? How many cards do I have to pick before I get a heart? This is going to be the geometric model's big main goal. And we kind of talked about this briefly in binomial model when we were talking about, do these meet the conditions? And we said one of them we'll learn about later. This is it. First success is geometric. Now, some examples: you flip a coin until you get a heads, you roll a die until you get a six, or you throw a dart until you hit the bullseye, kind of things like that. You're looking for the first instance where you would get your considered success. So there are 4 conditions for a geometric distribution. It shares 3 of them with our binomial random variable. Again, it has to be binary, meaning you have to have success or failure. You have to have 2 outcomes. That's the only option. Either it is what you want it to be or it's not. Now, I is going to be independent. Again, we want to make sure that one probability is not going to influence another, and hand in hand with that would be our success probability. We want to make sure that that doesn't change. So independent and constant probability kind of go together, because that's kind of just giving you your clue that your probabilities will not change from each event to the next. Now, where it differs, here it was the number of trials is constant or is fixed. Now it's going to be trials until first success. So we want, how many trials does it take until I get my goal, my success? Now, for the formula, we're going to build it up based on just a example, and then we'll kind of give it to you formally. We have a 6-sided die. We're going to let y be the number of trials until you roll a 6. So what is the probability that you roll a 6 on the first trial? Well, I know it's 6-sided. I'm going to assume 1, 2, 3, 4, 5, 6. So that probability is just going to be 1 over 6. Straightforward, nothing crazy. Now, what is the probability that you roll another number on the first trial, but then you roll a 6 on the second? So first trial is another number. So if it's a 6-sided die, that means it's a probability of 5 over 6. And then on the second trial, I did roll a 6, so that probability is a 1 over 6. Multiply these two together, general multiplication rule, and I get 0.1389. So it took 2 rolls until my first success. So that's kind of why it's falling in geometric. Then they ask, what is the probability that you roll another number on the first 2 trials, but a 6 on the third? Well, it's going to follow that same pattern. My first 2 trials are failures, and my third trial is a success, giving me approximately 0.1157 chance of this occurring. So this will continue on. We will continue on. What if it's the 4th trial? Then I would do 5 over 6, 5 over 6, 5 over 6, and then 1 over 6. So this will continue on forever, really. So I could have y equals 1, y equals 2, y equals 3, y equals 4, continued on all the way up to infinity, really, because it could happen, in theory. You could keep rolling the die and not get a 6 for a very, very long time. And so what would happen in our calculations is we would keep going with 5 over 6 until that last trial to get 1 over 6. So a big difference between geometric and binomial is, can y be 0? We always said with binomial, you're going to start your table at 0 because there is the probability of having no successes in your fixed number of trials. Well, in geometric, that can't happen because y, which is our random variable, is measuring the number of trials you need. And you're going to need at least one to have a success. So we always start our tables for geometric at y equals 1. So when do we stop the table? Like I just said, we don't. We can't. We can technically go forever without seeing a success, in this case, a 6 on a die. Now, is that likely? No, but in theory, yes, we could go on forever. And what pattern are we noticing? Well, we talked about how we're taking our probability of failure. So in this case, it would have been 1 minus 1/6, which gave us our 5/6, to the power of however many failures we encounter first, then times the probability of success. So this is kind of building up the formula for the geometric model. So give you a second or two to copy this down, and then we will talk about formula. Okay, so formula time. Again, I will give you the formula. The formula works continuously. Often with geometric, people prefer to just use the formula because it's quicker than going through the steps of their calculator and writing that stuff out. But again, both of them are accepted for AP exam grading. If you were to describe a geometric distribution with probability of success P, and K represents the trial where you get your first success, we still have that kind of notation for describing the model. So Y, given that it's geometric with a given probability, formula looks like this. Probability that Y is equal to K means you're looking for probability of the first success on the K trial, really. So if I wanted it to be like my first question, he rolled the 6 on the second roll, Y would be equal to 2. 1 minus P to the power of K minus 1. So that's representing our probability of failure raised to the number of failures. So if I had 2 trials, so K is 2, then that means I had to have 2 minus 1, at least 1 failure first. And then, of course, the probability of that single success for whatever random variable you're interested in. So this one's a little more straightforward. The reason why it's helpful to use exponents for your probability of failure, yeah, it kind of makes sense when it was like, oh, what is it for the second or the third trial? You can write that out. But sometimes they're like, what's the probability of rolling a 6 on your 20th try? You don't want to write out 5/6 19 times and then 1/6. So saves you a little bit of writing in this instance. So what is the probability that it takes you 5 rolls until you get a 6? Now, something that I do want to kind of clarify here, it does get confusing. When they tell us it takes us 5 rolls, that means my Y is going to be equal to 5. That means I get my 6 on the 5th roll. I know some students read it as it takes you 5 rolls and then you get a 6. That's not what they're saying. It's 5 rolls, you got your 6 on the 5th roll. So we're going to have the probability that Y is equal to 5. So that means if I got my 6 on the 5th roll, I had to have 4 failures first. So 5/6 to the power of 4, and then my success, which with general multiplication rule gives me approximately 0.0804. Again, I typically round to 4 decimal places just because it does convert nicely to percents in the event that they ask you to interpret. Because this would be like 8.04% chance of this occurring. Okay, what is the probability that it takes you 10 rolls until you get a 6? Again, 10 means I'm getting it on the 10th roll. So the probability that y is equal to 10. If I get it on the 10th roll, that means I had 9 failures. So 5 over 6 to the power of 9 times 1 over 6 gives me approximately 0.0323. Pretty straightforward here. Then we move on to different types of questions. What is the probability that your 6 happens within 3 rolls? So either you got it in 1 roll, you got it in 2, or you got it in 3. So that's like me asking, what's the probability that y is less than or equal to 3? Remember, these equal to signs are really important for these types of probabilities. So what I can do is I can calculate each individual probability and add them together. Add, add. So we know probability y equals 1 is just 1 over 6. Y equals 2 means we had one success, one failure, one success. 3 would be 2 failures, 1 success. When I combine all of those things together, I get approximately 0.4213. Again, with the cumulative type ones, you are adding those probabilities together. You wouldn't multiply them all together. So if I said, what's the probability that you get your 6 in 4 rolls or in 7 rolls? I would take the probability of y equals 4, add it to the probability of y equals 7. Anytime you get those or encounters. I know those sometimes come up in your MyLab assignments. Okay, what is the probability that it takes at least 4 rolls? So here they're asking us at least 4 rolls. So that means it could be the probability that y is greater than or equal to 4. Well, remember, anytime you are doing at least, you want to think of it as the opposite, because in this instance we could go on forever. We could get y is equal to 1,000,000 and keep going and going and going. So that's not the best way to approach it. Instead, you want to find the opposite. So I always kind of try to write a number line just so I can figure out where my cutoff values are. It's usually not a big one. It's just one where I can see, what am I including, what am I not. So I want at least 4 rolls. So this would be my cutoff. What's this probability? That's what I'm interested in. So I know that in total, all of these things have to add up to 100% or 1. So what I can do is I can take this piece, which is much easier to calculate, the probability of y being less than or equal to 3, and I can subtract this probability from 1 in order to get probability of at least 4 rolls. So it's kind of like doing the opposite and subtracting from 1, which makes it a little bit easier for us. Otherwise, you're calculating things up until the millions and stuff, and takes a long time. So 1 minus the probability of y is less than or equal to 3, which we just found, 0.4213. So I'm not even going to do any additional work there other than subtract, which gives me 0.5787. So anytime you have an at least question, always think of it as 1 minus the opposite probability. If it's just in terms of success, we usually, in like a fixed number of trials, we usually think of it as 1 minus the probability of none. But here, because we're dealing with cumulative stuff, I always suggest a number line helps. Don't have to do it, but it helps you visualize, well, what numbers can I find the probability of, and what am I looking for? So in our calculator, these are going to also have shortcuts like they did with our binomial type questions. For GeoMet PDF, we are looking at probability of y is equal to k. For GeoMet CDF, we are looking at a cumulative. Again, your calculator only computes less than or equal to. So you'll have to be careful and convert everything so that you are looking for less than or equal to values. These are all in the second bars menu, and we'll use them in just a second. They function exactly the same as our binomial PDF. The only thing it does not ask you is trials, because in geometric models, we do not have a fixed number of trials. So it asks you probability and what success do you want it on. I think in the calculator, it will say X, not K. So let's go ahead and try putting some of these to use. We have first, quick discussion, mean and standard deviation. For geometrics, they are a little bit different. For the mean, you are, just to be clear, I'm sure all of us know what the mean symbol looks like now. Mean, you're doing 1 over the probability of success. For standard deviation, it's going to be square root of 1 minus p over p. More than likely, they'll ask you for mean. Rarely do they ask for standard deviation, but both of these formulas are given to you, so you can use them. Just to be quick, mean is asking how many trials we expect to run before we get our first success. So if I find the mean, that's kind of what value I'm getting. Standard deviation is just that typical, how much does it typically vary or deviate from the mean. Example 6, to start her old lawnmower, Iris has to pull a cord and hope for some luck. On any particular pull, the mower has a 20% chance of starting. So my model, if it were to be given to me in symbols, I'm going to use y as my random variable, given that it's a geometric model with a probability of 0.2. Now, I will say they can mix and match the type of model you're using for each question. So I could use this, and maybe in different parts of the question, if it was FRQ, they might ask you a binomial question, they might ask you a geometric question. The big tell is, did they tell you how many trials there were? And did they say first success, or did they say until they get this? That's kind of the giveaway. So find the probability it takes her exactly 3 pulls to start the mower. So I'm doing the probability of y equals 3. So I'm going to do this in my calculator. So I'm going to open it up. For your geomet, you're still going to do second vars. This time we are going to go up to F. So geomet PDF is for when it's equal to, and I want exactly 3. So my probability of success is 0.2. My X value, which for us is K, what's the success they want, is going to be 3. And then I'm going to hit paste, and I'm going to hit enter, and it's going to tell me 0.128. Now I do want to show you that's the same thing as me doing her failing on the first try, failing on the second try, and then getting it on the third try. We get the same value. So you can use the calculator method. You can do it by hand with your calculator. Either way works. If you are doing it without writing out the formula, you do have to write your calculator input. Make sure that you remember to label your input values. And that gives me approximately 0.128. So PDF is for exact. It's equal to something. Now, find the probability that it takes her more than 10 pulls to start the motor. So, again, our calculator is only doing less than or equal to. So this question is asking me, what's the probability that y is greater than or equal to 10? My calculator can't do that. So I have to, again, work in the realm of what can I actually find. So I, a number line person, a physical, needs to see it to process it. Draw out a number line. It does not have to be the whole number line. It just kind of has to center around the value you're interested in. I want to see what's the probability that it's 10 or more. This is what I want. That's the probability that I am interested in. However, I cannot find it because this is going to keep going on forever and ever and ever. Now, I know down here it's starting at 1. I can compute 1 to 9 pretty easily. I can find this probability. This is the probability that y is less than or equal to 9. And I can just subtract that from 1. So that's what I do. 1 minus the probability of y is less than or equal to 9. Because my calculator can do less than or equal to. So I'm going to go to my calculator one more time. I'm going to do 1 minus second vars up, second vars, start back over, up to Geomet CDF, which is G. I'm going to tell it my probability of success is 0.2, and my value that I'm interested in is 9. Paste. So I'm doing 1 minus the probability y is less than or equal to 9. Hit enter, and I get 0.1342. So again, with our calculator, you do want to write your input. Do not forget to label P and X, and you get your, which I didn't box for this problem, probability. So be careful with that. They do like to trick you and give you something that's not necessarily doable in your calculator without interpreting it a little bit. Okay, last problem. How many pulls do you expect it will take for Iris to start the mower? So expect is going to be your big key. We are doing mean because it's expected value. So I'm just going to use the formula from up top. 1 over P, 1 over the probability of success, which was 0.2, gives me 5. So on average, we can expect it will take Iris 5 pulls to start the mower. Pretty straightforward. Nothing too crazy with mean and standard deviation for these types of problems. So shouldn't be too bad. You just have to make sure you're using the correct formula. You're not using binomial for geometric and geometric for binomial. That, I will say, is where people get tripped up the most.